It is time to start. Does anybody have any questions before we get started?
I have questions about the lab from last week.
Yes. I
The
think I saw you.
assignment,
Did you send me a text message or an email? Because I
I
remember
did,
somebody,
yes.
Christine. Gotcha. I just hadn't had a chance to reply to you yet. Refresh my memory of what the question was
So the assignment is telling us to import, use
from
10
the world
different
folder or
videos.
something.
Yeah, from the world folder. Where are we supposed to be getting those videos from?
Uh, if you watch the video that I did on the lab, you'll find that I put the videos directly in the lab module with it. So
So
there's
the
no
mod,
world folder. That's something that would be on the computers in our lab. What makes you able to do it at home is the addendum where it tells you to download the software. And then I mentioned in the video, the intro, that the videos were actually on the module with that lab.
yeah, I saw those on the module, but the
Mhm.
module only has like 5 out of the 10 videos that the assignment is asking for.
Uh, there should have been all of them, but I will definitely update that and I'll adjust the due date to be due like 2 days later, if there's any missing. So I'll take care of that. But yeah, they should all be there. I thought I'd put them all out, but I'll double check them. It might have been I put them all out, but I didn't. I hit the button twice, and that makes a difference between it publishing and not publishing. So it would be there when I look at it, but it wouldn't be there when you look at it. So I'm assuming that might have happened, but I'll take care of that tonight, and I'll definitely push the deadline back.
Okay, thank you. Do you
No
want me
problem.
to write in the chat which videos are not
If you
showing
know
up?
that'd be great. Yeah. That way I can make sure I don't miss any particular ones. So yeah, I know I have them all here. It's just a matter of whether I put them up or not, and that should have been done.
Okay, thank you so much.
No problem. Thanks, Christine. Sorry I didn't get a chance to get back with you yet.
That's okay.
Nathan, Samuel, Michael, anybody else have any questions? Good deal. All right, well, we're going into chapter three, and this is where we start using vectors. And in so doing, you might actually be encountering something you haven't covered before, even in pre-calculus. Trig portion. Specifically, we use unit vectors in the calculus-based physics course. So instead of just giving a magnitude and a direction relative to some coordinate system that you draw, we can actually give you vectors in terms of I hat, j hat, and k hat. I hat being a unit vector that points in the positive x direction, j hat being a unit vector that points in the positive y direction, and k hat being a unit vector that points in the positive z hat or in the positive z direction. Some people also call them x hat, y hat, and z hat. That's perfectly acceptable. The big thing is it is truly a unitless vector, so the units are not units of meters or anything like that. It literally means a magnitude that's exactly 1 unit. No 1 meters, no 1 Newton, no nothing like that. Because the way you can calculate a unit vector is you take any vector and you calculate its magnitude, and then you divide each component of that vector by the magnitude of the whole vector, and that'll make each of the components turn out to be such that the quadratic form, or excuse me, the Pythagorean theorem for a three-dimensional vector would be x squared plus y squared plus z squared. Take the square root of that, and that would come out to be exactly one. Again, one, not 1 meter, not 1 Newton, not 1 meter per second or anything like that. So that's one of the differences. We're also going to cover dot products, which most trig classes cover, but some don't, and we'll cover cross products as well, but that will not be done. Neither the dot product nor the cross product will be done yet. So I need to give you an idea what exactly vectors are, and to do that, I'm going to start off with telling you what scalars are. So let me go ahead and share my screen with you guys. This should pop up any second now. So first off, we're going to talk about a scalar. A scalar is a pure number or a denominate number. So denominate just means it has units. It has a denomination. In other words, just like when you say a bill is a $5 bill versus a $1 bill, that's the denomination of the bill. So a scalar is a pure number or a denominate number, and an example is speed. And I specifically use that example because it starts with the letter S, just like scalar does. A vector, I probably should have done that capital. A vector is an object. Well, that could have went worse. It's an object that has a magnitude and a direction. And an example is velocity. So velocity is a vector quantity, and again, just like scalar had an example as speed, which started with an S, we have a velocity, which is a vector that starts with a V, just like the quantity vector starts with a V. So that's a little mnemonic that'll help you. But more specifically, other examples for speed for scalars are pressure. There are actual ways you can define pressure such that they would be vectors, but in general, we treat a scalar pressure as a scalar. Others include pressure, mass, pi. Oop, there should be two S's in mass. Mass, pi. Well, that just made it look like man now, so that's just horrible. So, so pressure, mass, energy. So there's some examples of some scalar quantities. Others for the vector. And basically, you can sort of decide when something needs to be a vector quantity by realizing the vector quantity usually is defined in such a way that it's important not only to know how big it is, but what direction it's pointing in. So that's a really good indicator. But as I said, velocity is one of them, and that's usually the first one I mention. But the first one we'll actually deal with is displacement, which we've already talked about. Remember, displacement is a vector quantity, and it specifically can be imagined as a arrow that starts at your some object's initial position, and then the object can move off and do all sorts of things. And then when they get to the end of their motion, you can draw the vector, the arrow, from the tail being at the initial position and the head being at the final position. And then that straight line arrow is what we call the displacement vector. So that's another quantity that is a vector quantity. Another one is momentum, which we haven't learned about yet, and force, which you sort of know about, but you haven't really learned that much about it as well. So velocity, displacement, momentum, and force are some examples of vector quantities. And I gave you as a working definition that it's an object that has a magnitude and direction. To be honest with you, there's a little bit more to it than that. Specifically, vectors transform when you go from one coordinate system to another in a very specific way. And that's the criteria for it as well. Whereas the scalar doesn't change from one coordinate system to the other. That's actually what we call an invariant. So that shouldn't change at all if it's a scalar quantity. Whereas a vector literally changes its components to maintain its vectorness as it goes from one coordinate system to another. So that's a little bit more general definition of vectors. I'll also tell you that those rules that we learned in pre-algebra, like the distributive property, the associative property, the identity number, which was the number one, which you know, one times a times one is just equal to a. That's the property of the identity. There's also a property for the inverse, such that the inverse of a times a is equal to a times the inverse of a, and that's equal to just plain one. That's another thing. All those different rules that you sort of thought were goofy, but they could kind of like in high school or maybe in, later on in a more advanced college class that maybe you didn't get to take in high school, you learn that those rules could be used to solve an equation. So, for instance, one of the things you learned is that whatever you add to one side of an equation, as long as you add to the other, is fine. Stuff like that. Those are some of the tricks that we use. So, for instance, we use the idea that an object plus its opposite, its additive opposite or its additive inverse, is always equal to zero. And for instance, if we had 2x plus 3 equals 7, we would say, well, 2x plus 3, I want to get rid of that plus 3, so I do the opposite, which is subtract 3, but whatever I do to one side, I have to do to the other. So I subtract 3 from both sides, but the fact that I took 3 and added to it the additive inverse of 3 was one of the fundamental characteristics that we use to make it okay to solve that equation. The reason why is because those particular operations and properties, the distributive property, the identity property, the additive inverse, the multiplicative inverse, all those different quantities and rules that we use are part of a bigger idea. So there's something called an algebra, not algebra the subject. There's an object called an algebra, and that algebra includes things that obey those properties. And one type of algebra is a vector algebra. So all of those rules that we learned about distributive, associative, commutative properties, identity properties, that sort of stuff, we learned about numbers, they're going to apply to vectors as well. So in a more advanced class, if you get to take, for instance, linear algebra at the higher level, then they'll normally have a portion of that course is dedicated to you guys proving that something is a vector space and proving that an object is a vector and stuff like that. And that vector space is the space in which the algebra exists, and that algebra is the thing that we're talking about. So that just gives you a little idea where you're going from there. But with that in mind, what I want to do now is give you my archetypal example of a vector so that we can make some sense of what vector addition means and what scalar multiplication means and stuff like that. So let's imagine that you live in this little house right here, okay? And this little house has a front porch right here, and then it has some steps for you to get down to the sidewalk, and then you have a sidewalk, and then of course there's a road, and there's a sidewalk that goes across or next to the road, and I'm just including that just to make it more cityfied, and we can also make it a little more neater to walk to. So, for instance, if you start off in your morning walking out the front door, then this is the position A, say. Okay. Now, if you walk from A out to here, then this would be called position B, and the displacement vector would be an arrow drawn from A to B. So this blue arrow is a vector from A to B and represents the displacement from A to B. So that's your idea of what a displacement is. A displacement is a vector quantity. You can picture it as an arrow. You put the tail of the arrow at the initial position. You put the head of the arrow at the final position. And even if that trip that got you from A to B did crazy stuff like this, the displacement vector would still be that same D. Okay. Now, if you decided to take it to some other point, like one of those turnaround sections or something like that, and you'd say that's an intermediate point, maybe A point 2 or something, then you could draw a vector or an arrow from A to A point 2, and that would be the displacement from A to A point 2. And then you draw an arrow from A point 2 to B, and that would be the displacement from A point 2 to B, and so on and so forth. The big thing to understand here, though, is that is a model of addition. So, for instance, when I talk about multiple trips, then if I take a trip from A to B and then another trip from B to C and then another trip from C to D, then I draw those vectors in succession that way. And a vector that is drawn from the very initial position to the very final position is, in fact, the sum of those vectors. So if I now consider walking over here to point C, which I'll say is right here, then here's a vector that went from B to C, and that's point C right there. So that little dot's point C. And then I might say there's another dot down here, and that's point D. And that vector goes from here to here. So the displacement the displacement from A to D is the sum of the displacements A to B plus B to C plus C to D. Okay, so what do I mean by that? I mean by that this vector right here, which goes from A to C, is what we call R, and I indicate it's a vector by drawing the R, but then I put an arrow over top of it, and that is called the resultant vector. In other words, when you add two or more vectors, the sum is automatically called the resultant. Now, if I wish to label these vectors, I might call this first vector A, and this second vector B, and this third vector C, and I would say A plus B plus C is equal to the vector R, like that. So that's our model for addition of vectors. We imagine it as if it's a series of little trips from one point to another to another to another to another till you get to the end, and the sum of all those little vectors from one point to the next, and then from that point to the next, and then from that point to the next, and then that point to the final one, the sum of those little vectors is the total displacement that you get for the whole trip, and therefore that's an idea of how to add vectors. So, for instance, if I were to give you, I'm going to put it in a coordinate system. No, I won't even put it in a coordinate system this time. I'm just going to draw it outright. So, if I said, for instance, here's a vector A, okay, and then right at the head of that vector, I put the tail of the next vector and say this vector is B. So, notice the tail of B is at the head of A. The vectors are in head to tail position or orientation or whatever you want to call it. So when I have two vectors and the tail of one begins at the head of another, those vectors are said to be in head to tail formation. If you're just wanting the sum of those two vectors, then you just draw from the tail of the first to the head of the last. So in such a case of only two vectors, I really didn't have room to fit that word vectors in there, so I'm going to erase it to and put it on the next line. So if such a case of only two vectors is considered, then the sum is drawn from the tail of the first to the head of the. Now, normally we'd say the second or the last, but since this one only had two, I'm going to say the head of the second. So in this case, we could say this is the vector r equals a plus b. Okay. Now, you might recall from those rules of algebra that you learned before that a plus b is the same thing as b plus a. So we could also draw b first. I'll draw b this time in blue. And I seem to be going, I'm trying to make an exact replica of it. Let's see. It starts from a little bit over to here, and then it's going to go up 1, 2, 3, 4, 5 and a quarter plus a half. 1, 2, 3, 4, 5 and a quarter, maybe like that. So it's going to be roughly, and it also goes over a little bit more than. So this is an attempt to be an exact replica of B. I drew it by eye, so there's a good chance it's not going to be exactly B. Now I'm going to attempt to do an exact replica of A at the head of B, and I can cheat a little bit because I know where it's got to be, and that's A. So now you can see that it makes sense to say A plus B is equal to B plus A, because you're supposed to start from the tail of the first to the head of the last. And when I consider the blue vectors, I'd start at the exact same spot that I did when I was doing the black vectors. But this time, that is the tail of B, not the tail of A. And I draw to not the head of B, but to the head of A. So we can see now that you can take any vector A and another vector, A and B, and add them in either order you want. Of course, the associative properties also allow, just like in this case was the commutative property or something like the commutative property of addition, if you will. But that also gives us some ideas about vectors. It turns out that, in fact, when you're working with a vector, at least in terms of actual vectors in space, not a vector field, which we'll learn about later, then you can pick up a vector and move it anywhere you want as long as you don't stretch it or compress it. Okay. If you stretched it or compressed it, you're changing its magnitude. So you can't do that, because the obvious thing is that a vector has magnitude and direction. And if you change the magnitude or you change the direction, then it's not the same vector anymore, because that's its two characteristic properties. So you can move that vector anywhere you want as long as you don't stretch it or compress it. And also, as long as you don't rotate it, you don't want to change its direction. So you can move vectors along anywhere you want, long as you don't change their direction or their magnitude. So what I like to tell my students is imagine I took this vector B and I just treated it like it had a little loop on the end and I just dragged it along here until now it's there. That's something you can do. You can actually take the B vector and slide it along the A vector and reposition it. Similarly, I can take this A vector and imagine it's on a little loop, and I can slide it along B, and I'll get this other version of A right there. So we see that when you have two vectors that are head to tail, then you draw from the head of the first to the head of the last. But here's something else neat. If we look at this diagram, but not look at A and B in head to tail formation, instead we look at B right here and A right here, those two vectors are not in head to tail configuration. In fact, those two vectors are said to be in tail to tail formation. Okay, so now I'm going to write if we consider the blue B vector and the black A vector, we see, I'm going to write they with a THAY, they are in tail to tail configuration. So that's another terminology we need. We need head to tail, like you see the black A is with the black B, and like you see that the blue B is with the blue A. Those are head to tail. But if you look at the black B, or excuse me, the black A and the blue B, then you see that those two are tail to tail. And that tells us that there's a way to add vectors when they're tail to tail. If the two vectors are tail to tail, you complete the parallelogram. So oops, if I just had this vector and this vector, I would slide this vector along A to make that one, and then I would slide this vector along B to make that one, and that would be called completing the parallelogram. Then the sum of those two vectors is drawn from the common tail to the diametrically opposed opposite vertex. So now that I've given you that idea, starting from the idea of displacement, you can now hopefully graphically understand how to add vectors. So let me write down our big conclusions right now. So vectors, let's see, two, or let's just start with two. I'll talk about more vectors later. Two vectors in head to tail configuration or position are added by drawing a vector from the tail of the first vector and that might sound a little confusing, so I just want to remind you that is the loose tail. The other tail is tied to the other vector, so there shouldn't be any ambiguity if I just tell you the loose tail because we drew it like this, there's really only one loose tail, it's that guy, and there's really only one loose head, it's that guy. Okay, so two vectors in head to tail configuration are added by drawing a vector from the tail of the first vector to the head of the last vector. Now, I wrote the word last that time because I wanted you to understand that the generalizing this to multiple vectors is just a matter of drawing it to the head of the last vector when they're all tail head to tail, head to tail, head to tail. Okay. Right now, I'm just talking about two vectors, but if we had three, we'd just draw it from the tail of the first to the head of the last, which is the third. If we had four, we draw it from the tail of the first to the head of the last, which is the fourth, so on and so forth. So two vectors in head to tail configuration are added by drawing a vector from the tail of the first vector to the head of the last vector, which is also called the loose. Oops. I left off a O last time. The loose head. And let me fix that too. I don't look like a complete moron. So from the loose tail to the loose head, in that case, it would be basically this vector. Now, if you have access to, for instance, to AutoCAD or one of those type of drawing programs where you can type exactly what distance you want, exactly what angle you want, you can just put them head to tail and then draw another one, and it'll give you exactly the right answers. You could just click on the one that you drew from the tail of the first to the head of the last and find out what its length is and find out what its direction is, and that would be complete vector addition of the two vectors. So you can do that. For multiple vectors, for more than two vectors, addition, okay, I'm going to take that off. Addition is from tail of first to the head of the last. So, for instance, I could do A, B, C, D, like that, and then this would be the resultant. R is equal to A plus B plus C plus D, like that. So that's how we handle it in more general cases of multiple vectors. We just draw head to tail, head to tail, head to tail, head to tail. And when you're doing this in practice, like if you're actually trying to do it on like graph paper and you're trying to work it out mathematically, what you have to do is you draw the first vector's tail at the origin, and then you use a protractor to measure what angle from what axis. So, for instance, you might have an angle down from the positive x-axis, like I'd have to have for A, or you might have an angle that's up from the positive x-axis, like I'd have for B, or you could possibly have an angle that is measured from to the right of the positive y-axis. That could also be a way to specify B. You could also figure out an angle to the left of the positive y-axis, which would be like C, and you could find an angle, let's say, to the left of the y-axis to find vector D. But the way you'd go about doing it is you draw that first vector with the tail at the origin, and then at the head of that first vector, you draw another coordinate system, another x, y, so that the positive x direction is exactly parallel to the original positive x direction, and the positive y direction is exactly parallel to the original positive y direction. And then you'd measure from that one of those axes, you'd put the tail of the second vector at the origin of that coordinate system, which obviously is at the head of the previous vector. And you keep doing that over and over again. And that would allow you to use a protractor and a scale. You'd have to, of course, set some scale where, 1 centimeter on paper is equal to 100 newtons in reality or something like that. You could use some kind of scale and then draw it all out. And then if you're very precise, using like a thin leaded mechanical pencil, being very persnickety about using your protractor and your scale and making sure you put the head of the or excuse me, put the tail of the next vector exactly at the head of the previous vector, and that you draw the coordinate systems exactly parallel, and then measure your angles, draw another vector, and then measure angles, draw another vector, and then you draw a vector from the original tail to the final head. You could then measure that vector and measure the angle that vector makes with the positive x-axis or the positive y-axis or to the left of the positive y-axis, whatever you want to do, and that would give you a way of determining the magnitude and direction of the resultant. And that's what we mean by adding vectors. When you add two or more vectors, you should be able to give me back a vector that has both magnitude and direction. And you could also specify it, like I told you earlier, with those I hats, J hats, and K hats. We haven't done that yet, but I just wanted you to first understand graphically how we go about adding vectors. So that's how you do two vectors that are head to tail. Now I'm going to give you how you do two vectors that are tail to tail. Two. If two vectors are tail to tail, then you can slide one vector along the other, or let's do it. I'll be more specific. You can slide the first vector along the second, and then slide the second vector along, oops, the first, creating a parallelogram. The sum or resultant is then drawn from the common tail. Oops, I crossed my L instead of my T. So it's drawn from the common tail to the opposite vertex. So what do I mean by that? Let me show you real quick. So I'm going to start off drawing my two vectors as if they're head to tail. So here's my vector A. Now, if they were head to tail, then obviously I'd want to put B at the head of this. And I just made a mistake when I said I'm going to draw them head to tail. I meant I'm going to draw them tail to tail. So I put A there, and now I'm going to put vector B right here. And you can see they're tail to tail because here's the tail of B, boom, and here's the tail of A, boom, right? Now what I'm doing is I'm trying to slide vector B along A, or in this case, like said, slide the first vector along the second. So I can imagine sliding this A vector along B like that. And then I can imagine sliding the B vector along A like this. Notice I'm just drawing these multiple lines so that I can sort of attempt to keep them parallel. But ultimately, what I'm supposed to have done is now this is vector B, and now, oops, now this is vector A. So now you can see I have completed a parallelogram. This side is parallel to that side. This side is parallel to that side. That's what makes this a parallelogram. And the sum of the two vectors is drawn from the common tail to the opposite vertex. So this is the vector A plus B, which is equal to the resultant or the sum. Okay. Now, if you had three vectors that were tail to tail, what you could do is take any two of them and complete the parallelogram for them too, and then draw the sum of those two, and then that sum vector will be tail to tail with the third vector. So now you can complete the parallelogram for that new vector and the original third vector, and that would give you a tail to tail vector or a vector going across the diagonal of the parallelogram, and that would be the sum of the three vectors. So for instance, let me show you in smaller detail. Let's say I have this vector, and this vector. Let's say this is A, this is B, and this is C. So it doesn't matter which three I use or which two I use first. I'm going to go ahead and complete the parallelogram with A and B. So I'm going to go, oops, I want to do that in a different color. Sorry about that. I'm going to go, something like that. And then I'm going to go something like that. So what I have now is another version of vector A and another version of vector B. So now I can say that this vector is A plus B. Now I can complete the parallelogram between A plus B and C by, now I'm going to take this purple vector and try to draw parallel to it, parallel to it, parallel to it, parallel to it. And now I'm going to draw one parallel to the green vector, something like that. And now we can say this must be the new A plus B vector, and this must be the new C vector. So now we can finally say that this vector is A plus B plus C. So that's the way you could do it. No one would ever do that, and I would never ask you to do that. I just wanted you to know that in general you could do that way. Normally, or let's say more realistically, on a test, there's a high probability that I'll give you two vectors drawn tail to tail or head to tail, and I'll say on that drawing, draw the sum of those two vectors. So that's something you need to be able to do, and you need to be able to do just like I did it here. Notice I didn't draw the vector off to the side, not touching the original vectors. No, I drew the actual sum right there touching the original vectors. I didn't draw it off some distance away. If you do that, you're going to lose points, okay? And if you sort of don't show me where the head of the resultant is, like you draw the line, but you don't make it clear that there's a head at one end versus the other, you're not going to get credit for that either. But this is something you should be able to do. If you're given two vectors in head to tail position, then you should be able to draw on those two vectors the sum of the two. And if you're given two vectors in tail to tail position, you should be able to draw the vector sum of the two. Let me show you one more example of that, or two more examples, one head to tail and one tail to tail. So for instance, here's vector R and here's vector C. The sum of those two, since they're head to tail, is drawn from the tail of the first to the head of the last. So this is the resultant vector is equal to R plus C. Let me draw another one when they're head to tail, or tail to tail, excuse me. So for instance, this vector might be Q and this vector might be U. Okay. When they're head to tail, we draw from the tail of the first to the head of the last, but when they're tail to tail, we complete the parallelogram. So what I'm going to try to do is complete the parallelogram by drawing a series of green lines that are hopefully somewhat parallel to Q, and then drawing a series of parallel lines that are hopefully parallel to U until I get to the very end right here. And now I'm going to say that this is the same thing as the U vector, and that this is the same thing as the Q vector, and therefore this is the vector R is equal to Q plus U. So that's what I mean. Notice I would give you just those two red vectors, U and Q, and I would expect you to draw the parallelogram like I did and then draw the black vector right where it is like drawn here. Same thing with the first diagram. I'd draw the red, or excuse me, the green R vector and the green C vector, and then you would fill in that R equals R plus C vector right like that. If you had it disconnected, if you drew it over here, I'm not going to give you credit. If you drew it over here, I'm not going to give you credit. If you drew it over here, I'm not going to give you credit. Okay, you've got to actually draw it tied to the original diagram. Anybody have any questions on that? Okay, so that's how you add two or more vectors graphically if they're head to tail or tail to tail. Now, there's another vector operation that we should know, and that's subtraction. That's a little more complicated. But before I can do subtraction, I've got to give you some idea of what scalar multiplication by a vector is. So, multiplying a vector by a scalar. So for instance, remember we're using displacement as our model vector. And the displacement is an arrow. It's actually a vector, but we treat it as an arrow. It's an arrow drawn from your initial position to your final position. If I told you that one day I did a certain displacement and the next day I walked twice as far, then you should have some idea that the displacement for the second day is in some sense two times the original displacement. So if the first day the displacement was called lowercase d vector, then the second day the displacement vector would be called 2 times lowercase d vector. Okay, so hopefully that gives you some idea of what we mean by multiplying by a scalar. Uh, with that in mind, I think it becomes pretty clear that you're going to make the length of the vector twice as long. Now, additionally, if you took a certain displacement, let's call it lowercase d, and you walked from your front porch to some distant location, I bet that you would understand If you walk back the exact same way, you would get the negative of your original displacement. In other words, your trip back would have a displacement vector that's exactly the multiplicative inverse of the original displacement. So, for instance, what we just did was maybe I said, here's vector D, and now I'm arguing that vector 2D would be at exactly the same angle, but it would be twice as long. That's exactly what scalar multiplication is. But I also said, what about if I did displacement D1 and then I followed that with the return trip back, and I would say this is vector D2, but I think you would all agree that displacement 2 is the additive inverse of displacement 1. And you remember from algebra that the additive inverse was the negative of a quantity. In other words, the additive inverse is what you added to a number to get zero. Just like if you took a displacement of D1 and then you took the return displacement back, you expect the displacement to be zero. Therefore, you expect D1 plus D2 would equal zero. And the only way D1 plus D2 equals zero is if D2 is the negative, the additive inverse of the original one. So D2 is in fact equal to negative D1. Okay. So what we figured out now from that reasoning is that evidently, if you multiply by a scalar, that's going to change the length if the scalar is some number other than one. So, for instance, if the scalar is 2, it's going to make it twice as long. If the scalar is 3, it's going to make it 3 times as long. If the scalar is 1.78, it's going to make it 1.78 times as long. So, I'll say the magnitude of the scalar, oops, can be multiplied, oops, can be multiplied, oops, I should say applied, I-E-D, P-L-I-E-D, by the original magnitude of the vector to get the new magnitude of C times A. For instance, if your vector was A, and you want to multiply it by C, you take the magnitude of C and multiply it by the magnitude of A, and that would be the vector, that would be the magnitude of the new vector C times A. Okay, so that's what we showed when I took the D and multiplied it by 2. That made it twice as long, so on and so forth. The other thing we learned is that when we multiply by a negative, if the negative happens to be a -1, then we don't change the magnitude at all because 1 times any number is still that same number. So that's why D2 and D1 had exactly the same magnitude. But the fact that the D1 was multiplied by -1 to get the D2 made the D1 be turned around to make the D2. So if the number or if the scalar is a negative, then the direction of the scalar product of or I should say the vector of, or excuse me, the direction of the vector multiplied by the scalar, the then the direction of the vector multiplied by the scalar will be 180 degrees from the original vector's direction. So if the scalar is a negative, still the same rules working. So if it's a -2, it's going to get twice as long. If it's a -3, it's going to get 3 times as long. If it's a -1.78, it's going to get 1.78 times as long. But the fact that it's negative means the tail is going to go from that end to this end. So for instance, if I drew, let's say this vector right here is vector A, then vector 2A would be from here to here. That would be vector 2A. Vector 1/2 A, actually, got to be a little closer, a little careful with that. This would be vector 1/2 A. Notice it's half as long, but it's exactly still parallel. The way we know that is it only went over to the right half a block, whereas it went up a whole block. Now, also, if you wanted the vector -2A, then it would go across 2 and spread just 1 and then go across 2 again like that. So this vector would be -2A. And then, of course, if you wanted 3A, that would be from here to here would be A, to here would be 2A, to here would be 3A. So this is vector 3A. Does everybody follow that? Anyone have any questions on scalar multiplication by a vector? All right. Now I've got to talk about, thanks, Christine and Mihak. And now I got to talk about subtraction of vectors because in order for us to do subtraction of vectors, you needed to understand what happens when you multiply -1 by a vector. So, uh, subtracting vectors. So here's a blast from the past that you probably thought was stupid and ridiculous. I know I did when I was taking pre-algebra and then algebra 1, and we were introduced to this weird thing. They said, and I kid you not, this is exactly what they said. A minus B is defined to be A plus the opposite of B. Do y'all remember that? Does that seem familiar? It seemed like the stupidest thing in the world. And it is to some extent, but it really is the definition of subtraction. In order for you to have an algebra, you have to have all those rules, and those rules included the existence of an additive inverse for every number that you have. You don't necessarily have a multiplicative inverse for every object that you have in your algebra. For instance, there is no multiplicative inverse of 0 in the number system because 1 over 0 is undefined, right? Whereas normally it's the reciprocal that is the multiplicative inverse. So you don't have to have a multiplicative inverse, but you do have to have an additive inverse. And the additive inverse is the what we call the opposite of the object. So in terms of vectors, we can make that the same thing. We can say A vector minus B vector is equal to, or specifically defined as, that's what we use the 3 bars. When you put the 3 bars up there, that means defined as A vector plus the opposite of B vector. So you probably saw that when two vectors are head to tail, it was really easy to add them graphically. You didn't have to do anything except draw an arrow from the tail to the loose head. However, when they were head to tail, you had to do some stuff. You had to complete the parallelogram and then draw the vector from the common tail to the common head, or from the common tail to the diametrically opposed vertex of the parallelogram. Now, watch what happens when I do two vectors head to tail and I'm doing subtraction. So let's say we have vector A like this, and then I have vector B like this. That's in our, or actually, you tell me, is this head to tail or is this tail to tail configuration? Head to tail. Thank you, Christine. I just got my chat up there. Y'all can go ahead, by the way, and oh, thanks. I see your note too, Christine. Thank you. Y'all can go ahead and chat me your first and last name too for roll, just so I have track of who came, even though, again, you're not required to be here. It's completely optional. So, how do we go about doing A minus B? If I want A minus B, I need to add A to the opposite of B. Okay, so I should go ahead and create the opposite of B, which the opposite of B would be the same thing as B, except it would have the head at the opposite end and the tail at the opposite end. Now, you see, when I did it in place like that, that wasn't very helpful because now I've got two vectors head to head, and we never learned anything about head to head. But we did learn that you can move a vector by sliding it, moving it around or whatever, as long as you don't rotate it, which would change its direction, as long as you don't compress it or stretch it, which would change its magnitude. So now I can just imagine drawing this B vector repeatedly parallel like this, and now I get negative B is right here. And of course, I want to be careful, so I need to make sure it's the right length. So I'm also going to imagine moving the A vector to the other side just to complete the parallelogram, if you will. Oops, I missed it by a little bit there. So this is A here. And then you can say A plus negative B. Now I have A and negative B in tail-to-tail configuration. And when we try to add two vectors in tail-to-tail, we draw from the common tail to the diametrically opposed vertex. And that would mean that the subtraction vector is right here. This is A minus B. So when I actually put the vectors head to tail in a subtraction, that made me have to complete the parallelogram. So it was sort of like, yeah, I got away with something by doing the head to tail vectors in addition. I got an easier problem. But when I did the head to tail vectors in subtraction, I had to do more work. So it's sort of like it equals out on the two sides, addition and subtraction. Now I'm going to show you what you do when you have two vectors that are tail to tail and you want to subtract them. So now let's see. Here's vector A, and here's vector B. And I'll do A minus B again. So A minus B involves me finding the opposite of B. So I'm just going to draw a red vector right beside this, and I'm going to put the head at the other end. And now I see I get negative B. And now you see I've got negative B in head to tail formation with A. So this one turns out super easy. Oops, I wanted that to be in purple. This one turns out super easy. I just draw this right here, and this is the vector A minus B. Okay, so that's how you subtract vectors. And be advised, there will definitely at some point be a test where you're given two vectors that are head to tail. are you're given two vectors that are tail to tail, and I ask you to draw the sum of those two on the diagram. I'm also going to do it for the difference of those two. I'll say A minus B, and in one example, I might say B minus A. All of those are fair game. Okay, so you've got to be able to do this just like I did this here. Anybody have any questions on that? Thank you, Michael. All right, so I've sort of covered all we need to know about vector algebra when we add vectors to one another, when we subtract a vector from another, when we multiply a vector by a scalar. That's all vector algebra. And that's the bare minimum of what we need to learn now. The thing we haven't learned is how to represent a vector or how to write a vector. So let me do that now. How do we specify a vector quantity? Okay. So, for instance, we could say vector A is equal to 14.14 newtons at 45.00 degrees. Notice the necessity that we have to have is a vector is a quantity that has a magnitude and direction. So bare minimum, you need to give me enough to find out the magnitude and direction, or you specifically need to give me the magnitude and direction. Okay. So I just did that. I said the vector A is equal to 14.14 newtons. That's a unit of force, by the way. And then I use the at symbol, which is just shorthand that we sometimes use in physics to indicate the direction. And I just blindly said 45 degrees. What you have to understand is that when I just say at a certain angle, then I'm using the standard position that you learned in your pre-calculus trig. Specifically, a theta being a positive angle is measured counterclockwise from the positive x-axis. If that angle happens to be a negative, it's measured clockwise from the positive x-axis. So now what I can do is draw this vector, and I'm going to show you another way that we can actually specify it once we're finished with it. And what I'm going to do is decompose this vector into x and y components. So this is going to be my x-axis. This is going to be my y-axis. That means the positive x direction is to the right, the positive y direction is to the left, the negative x direction is to, or excuse me, the positive y direction is up. I don't know why I said left. I was thinking of the next part. The negative x direction is to the left, and the negative y direction is to the downward direction. So all I have to do to draw this vector is I have to split the uprights because 45 degrees is halfway from horizontal to vertical. And then I need to specify the vector by drawing it the appropriate length. I'm not really set up a scale here, but that's okay because the scale will be set by whatever the heck I choose it to be. So the magnitude here is 14.14 newtons, and this angle right here is 45.00 degrees. And I did 45.00 because I wanted to have the same number of sig figs as the magnitude had. So this is our vector A. So everybody now sees what the 14.14 newtons at 45 degrees means. Now, I can break this up into x and y components because that's the way we add vectors most of the time. When we add vectors, we break them down into their x components, their y components, and their z components, and then we just add like components because all the x's are directions that are either pointing to the right, which would be a positive x direction, or to the left, which is a negative x direction, and they just add like positive and negative numbers. So x components of vectors add to other x component of vectors to give you the new x component of the vector that is the resultant. Similarly, there can be a y component of a vector that's added with the other y components of the vectors that gives you a new y component of the resultant. And similarly, they could be a z component as well. But and there's a lot of work to be done there, but we're not going to do a lot with it because it's just one extra step. It's too much of a pain to draw. That's the main reason. So let me show you what the x component is. Uh, if you imagine the line x is equal to 3, for instance, you would see that the line x equals 3 would be a vertical line. X equals 3.5 would also be a vertical line. So if you imagine a vertical line hitting the end of the a vector, let's say right here, boom, boom, boom. I'm going to do that with a different color. Let's say we imagine a vertical line that just skims across the tip of it, then the place that crosses on the x-axis will be the length of the x component. So this distance from here to here is the magnitude of the x component. And I'll put absolute value bars on it just to remind you it's the magnitude. Okay, we can treat the component as if it's a vector, but sometimes we also treat it as a scalar. So just be careful. Occasionally I'll say the x component and I mean a vector, and sometimes I'll say the x component and I mean the magnitude of the x component. If I wanted it to be the vector x component, it would be this little vector right here. So I would call this a sub x, and since it's a vector, I'd have to put the vector bar on it. Uh, if I was just talking about the magnitude, I would just call that a sub x with no vector symbol. Now, if you want to know the y component, we have to imagine doing the same thing, only this time instead of drawing a vertical line, we're going to draw a horizontal line that just clips the end of the vector. And then this distance from here to here is called the y component. And specifically, that's the magnitude of the y component, like we said before. But I could also make the y component into a vector quantity, and it would be this straight little vector right here. And this would be a sub y with the vector symbol over it. You might notice that we could also put the a sub y over here. And the difference is when I put the a sub y over here on the right, then I'm picturing the a sub y plus the a sub x as adding tail to tail. Whereas if I look at the other version of a sub y with the a sub x, in that case, they're tail to tail, whereas the other one, I think I said tail to tail last time, I meant head to tail. But the ay here with the ax here is tail to tail. The ax here with the ay here is head to tail. So those are the components. Now, how do we find them? Well, we don't have to think about it being vectors. We just have to think about it making a right triangle, because a right triangle is pretty easy for us to do. And in fact, I have a mnemonic. I use some old horse came a hopping through our alley. That's what I use. A lot of people use so, ka, toa. That's acceptable as well. But what it means is the sine of the angle is equal to the opposite side over the hypotenuse. The cosine of the angle is equal to the adjacent side over the hypotenuse. And the tangent of the angle is equal to the opposite over adjacent. So with that in mind, I can look at this and I can say the sine of 45.00 degrees is equal to opposite. Now, remember, with a right triangle, there's a 90-degree angle in it. And if you draw that 90-degree angle, it looks like that. That looks a little bit like an arrowhead. And that arrowhead is pointing at the hypotenuse. That's another thing that can help you. Locating the 90-degree angle in the right triangle allows you to draw that right angle, and that right angle acts like an arrow pointing to the hypotenuse. So that tells us the hypotenuse is the 14.14. The opposite is the side that's not touching the angle. So that has to be a sub y. And here I'm going to use the magnitude a sub y over the hypotenuse, which is 14.14 newtons. So from that, I can say that a sub y is 14.14 newtons times the sine of 45.00 degrees. And that would give me, using my calculator, making sure it's in degree mode, I'm going to say 14.14 times the sine of 45, and that gives me 1.00. Actually, it gave me 0.999. Actually, it gave me 9.998. So this is going to be 10.00 newtons. That's what I rounded it to. It's 9.998 is really what it came out to be. But that's close enough to call it 10.00. Similarly, we can say the cosine of 45.00 degrees is equal to adjacent over hypotenuse. The adjacent is the side that's touching the angle, so that's a sub x over the hypotenuse, which is 14.14. So we get that the y component is 14.14 newtons times the cosine of 45.00 degrees, which gives me 10.000 newtons. Again, it comes out to be 9.998 or something, but that's close enough, so I'm just calling it 10. So that's how you decompose a vector. This is called vector decomposition. You're breaking the vector down into components. Now, that also allows us a new way of writing the vector, and now I want to show you that. We could also say that a vector is equal to 10.00 newtons in the I hat direction plus 10.00 newtons in the J hat direction. So that's two completely independent but completely analogous or completely equal ways of specifying the vector A. We just remember that if the component points to the right, meaning the x component points to the right, according to the way we've drawn our diagram, that's the positive x direction, so I'll put a positive 10. If it was pointing to the left, I'd put a negative 10 times I hat. If the y component was pointing up, I'd put a positive 10.00 newtons times the j hat. But if it was pointing down, I'd put a negative 10.00 newtons times j hat. Similarly, if I had a component in the z direction, I would put a k hat with that. So the unit vectors we use are I hat, which is also equal to x hat. There's j hat, which is also equal to y hat. And there's k hat, which is also equal to z hat. Now, we could also write this vector A a slightly different way. I could, for instance, write vector A as, and this is a way that just saves you a lot of writing. So, when we're writing a triple, like a point in three space, we write left parenthesis X, comma, Y, comma, Z, right parenthesis. Well, when you're doing a vector that starts at the origin and ends at X, comma, Y, comma, Z, then you write it like this. In this case, it'd be 10.00 newtons, 10.00 newtons, and 0.00 newtons, like that. So that's another way we could specify the A vector. And that one's nice because you don't have to take the time to write I hat, J hat, and K hat. Not only that, and this is the reason I gave it to you, the I hat can also be written as I hat is equal to 100. The J hat can be written as 010, and the K hat can be written as 00. 0, 1. And notice those are exactly 1. Notice they didn't have newtons on it or anything like that. Anybody have any questions on that? All right. So, what I'm going to do now is I'm going to show you how we go about adding vectors. You'll notice in the week 3 module, I did put up a couple videos, one of which is called the world's greatest vector addition problem. And it's really not the world's greatest. It's me sort of paying homage to the Elf movie when Elf took his date to a coffee shop that he had discovered, and it said the world's greatest cup of coffee. And Elf was really excited about it because he really thought that it was literally the best cup of coffee, but it was just a crappy cup of coffee. So, anyways, I'm doing it like that. The reason why I said it's a good version is because I specify the vectors in sort of all the ways that I could specify vectors, so that you'd see how to handle each case. And the ways we specify them are usually magnitude and direction. We can do it with I hats, J hats, and K hats, but that's too trivial. That's too easy. So I usually don't give you vectors that way. I give you them in terms of magnitude and direction, but then I use a couple different ways to specify the magnitude and direction. So let me show you that now. So a vector addition problem. What is A plus B plus C plus D? That's our vector problem. Now I'm going to write down what those vectors A plus B plus C and plus D are. In other words, what are those vectors A, B, C, and D? So A is going to be the vector I just talked to you about. That's 14.14 newtons at 45.00 degrees. B, on the other hand, is going to be 20.00 newtons, and that one is at 30 degrees, and this is south of east. So I write S of E, that means south of east. I'm going to explain that in a second, but I just want you to know that S of E means south of east. This is also the same as negative 30. Because the east is normally considered to be the positive x-axis. And if I go 30 degrees north of east, that would be what we normally call positive 30. But if I go 30 degrees south of east, then that's a clockwise rotation from the positive x-axis. That's why I called it a negative 30 degrees. Now I'm going to look at vector C. And vector C is going to be 25.00 newtons at 53.13 degrees, and this time it's going to be west of north. And then finally, vector D is going to be 40.00 newtons at compass heading 240 degrees. Oops. Okay, so those are sort of the ways that we can specify vectors. And in order for you to make some sense of that, I need to draw like a x and y axis. So I'm going to draw a vertical line to represent our y axis. I'm going to try to let the program do that a little neater for me. And I'm going to start with my x axis pointing this way. So here's my x axis. Here's my y-axis. But in addition to that, the y-axis is also the north direction, and it's also a compass heading of 0 degrees. Okay? So the y is the north direction, It's also a compass heading of 0 degrees. The X is the east direction, but it's also a compass heading of 90 degrees. This is the south direction, but it's also a compass heading of 180 degrees. And this is the west direction, but it's also a compass heading of 270 degrees. So all of that is the kind of stuff you need to know. Now, I need to develop a scale that I'm going to use with this one. And ideally, I'd like it to be able to fit uh, as we have here. So I want it to fit on this paper. So normally we would start straight from the origin, and I think I might have put the origin a little too small because I'm going first quadrant, then I'm going to the fourth quadrant, and so on and so forth. So that's a little bit of a problem. All I have to do is take this stuff right here and pull it up further. Let's say cut. Whoop, that did not work. Let's say paste. Okay, so that didn't turn out how we wanted it to, but I think we can recover anyways. That'll be good enough. So I'm going to put it in the middle. And just remember the top already said that north. We still see it there, north, the compass heading 0 degrees. So the first thing I'm going to do is draw a vector that is at 45 degrees. And actually, I'm going to move this y-axis ever so slightly by erasing it. I want it to be actually on the line as opposed to mid-center between the lines, so I'm going to get rid of that. But now I'm going to draw it right here. And the program should make that straighter. Oops. That's good enough right there. And I'll put my little point here so everybody knows that's the positive. Now that first vector A is at 45 degrees. So what I'm doing is I'm going to use a straight edge to draw a line from the origin through each of the corners of those little rectangles. And it's really a pain because this surface is so slippery on an iPad. So when you go to try to draw something like this, the actual ruler slides everywhere. So you can see that's roughly 45 degrees. But now I also want the magnitude to be a reasonable scale. So I'm going to try 1 centimeter is actually 1 Newton. So I would need 14.14 millimeters. And that's a little too short. So maybe I'd say 1 Newton is equal to 2 millimeters. That would be 28.28. That's a little better. So when I look at this, the 28.28 would be roughly, there's 29, 28.28. That's roughly where the end of vector A would be. So there's vector A. Now what I have to do is imagine another coordinate system right here with the x-axis that way, oops, and the y-axis that way. Okay. Luckily, I can use the lines of the graph paper to indicate this. But in this case, the second vector B, that was A that I just drew. The second vector B is supposed to be 20 newtons at 30 degrees south of east. So now I need to go down 30 degrees. That's where I pull out my protractor, which I have, and I'm going to mark off 30 degrees from horizontal to the right. And I'm making sure the circle in my compass is at the head of the purple vector. And then I'm going to mark off the 30-degree mark some distance away, and then I got to draw a line to that and then shorten it according to the scale. So 30 degrees would be this point right there. So now I can draw this vector from here to here. That looks pretty good. Now I'm using the scale of 2 millimeters is equal to each Newton. So 20 is going to become 40. And that means I want 40 millimeters, which would put the end of this. Oops, that did not help. There you go. Got to watch out. Sometimes you expand that it changes the scale and everything will be jacked up. So that's the 40. So that means the head of my vector, B, is right here. This angle is 30.0 degrees. This angle was 45.00 degrees. So now I have vectors A and B. Now I need to draw another coordinate system at the head of this vector. So there's my x-axis and there's my y-axis. This third vector is west of north. So I've actually got to draw it to the left of that vertical axis, and specifically it needs to be at 53.13 degrees. So I'm again using my protractor, lining up the center of the protractor circle with the end of the arrow, the blue arrow. I've got that set up pretty well. Now I'm trying to go 53.1 degrees. So that's going to be roughly right where I put that little dot. Not a very wonderful one because it hits in kind of a difficult spot. But this vector I'll make red, and I'm going to try to draw it from the tail of that ahead of that last vector to that dot, which should be right there. So that one is 53.13 degrees. Like that. And this vector is supposed to be 25 newtons. So I'm going to make that into 50 millimeters. And of course, 50 millimeters would suggest its end is right here. So I'm now going to write the head of this vector as right there. So I've got that one. And now I've got to do vector D, which is 40 newtons at a compass heading of 240. So compass heading of 240 means I go to due east, which would be 90, and then due south, which would be 180, and then I add another 60 degrees from due south, and that would be my 270. So, or excuse me, my 240. So I'm going to take and now put another coordinate axis right at the head of this vector. Oops, I'm going to do that black. So there's my y-axis and there's my x-axis like that. But now I want to go 60 degrees to the west of south because 240 is 60 degrees west of south. So I'm now going to take the center of my protractor and again align it at the end of this last vector. And I'm taking and measuring 60 degrees from straight down, and that gives me a mark right there. So now I'm going to draw the vector. This time I will draw this vector in green, and I'm going to try to go from the head of that red vector down to this black line. And that's roughly it. Now that one's supposed to be 40, so that means 80 millimeters. So I'm going to go ahead and try to measure off 80 millimeters. And right here I have the 80. Ooh, the 80 just barely. I'm actually a little bit short, maybe. Yeah, it's a little bit short. It should be right there. So this one is 60 degrees, like that. And what I have now is that the resultant of these should be, let's draw a vector that's going to be black, because I haven't used that one yet. The vector resultant is from the origin, which is the tail of the first vector, to the end of the green vector. So this is R equals A plus B plus C plus D. Okay. Now, what I can tell about this is the length of this vector appears to be 54.9 millimeters. But our scale, remember, is one, or excuse me, 2 millimeters is equal to 1 Newton. So if I take 2 millimeters divided under 1 Newton, then 54.99 becomes 27.45 newtons. And the angle, by the way, appears to be, I got to make sure it actually hits. So I've got to give it a little extension here, and it looks like this angle is 12.2 degrees. 2 degrees, that's 12.2 degrees south of west. So that's what my resultant is graphically. So R vector is equal to 27.45 newtons at, in this case, I could call that, uh, if I did the standard position, it would be 90 degrees, 180 degrees, and then another 12.2. So that's 192.2. So I would write this as 192.2 degrees. I could also write it as 27.45 newtons at, in this case, I would say a compass heading of, what's 270 minus 12.2? 270 minus 12.2, just to keep from making a careless mistake, is 257.8. So, yeah, that would be it. At compass heading 257.8 degrees. That's another way of writing it. I could also say it is 27.45 newtons at 12.2 degrees south of west, which is what we'd already worked on. We could also call that 77.8 at 77.8 degrees west of south. So that's various ways we could do it. Now, what we really need to do is work out the individual components, which we can see from here. The A vector, which was that purple one, that would have a positive X and a positive Y. So we already know A would equal 10.00 newtons for the X component. And for the Y component, that would be 10.00 newtons. Vector B, we can see that's going to have that's the blue vector, by the way. Vector B is the blue vector, and that's going to have a negative Y component, but it's going to have a positive X component. And the way we work that one out is I know that this is 30 degrees, and I know that this magnitude is 20, like that. So this is B sub Y should equal some negative, and this is B sub X should equal some positive. And all we have to do is take 20 times cosine 30. So 20.00 newtons times cosine 30.00 degrees is equal to 17.32 newtons. And B sub Y is going to be negative 20.00 newtons times the sine of 30.00 degrees. So that's going to give us 20 times sine 30 and that gives us negative 10.00 newtons for that one. So now I can write the x component as 17.32 newtons, and I can write the y component as negative 10.00 newtons. Now, vector c is the red one. You can see in that case, I get a negative x and a positive y. So I'll put those signs over here. Notice how I'm never using angles bigger than 90. I don't recommend you using angles bigger than 90, and I don't recommend you using positive and negative sign, or I don't recommend you using negative signs for angles or negative signs for the sides. You need to pick them out like I'm doing here. So for instance, the fact that I had to go to the left, oops, I didn't mean to do that. I meant to do that with my pointer. Okay, so going from the tail of the red vector, I have to go to the left, which is the negative x direction, and then I have to go up, which is the positive y direction. So that's why I got negative and positive. If I chose to do it the other way, I'd get a positive y direction, but I'd still get a negative x direction. So that's why there's no ambiguity in which way I do it. In this case, I'm going to have to take uh, the magnitude of the vector, which is 25 newtons, and I'm going to multiply it by the sine to get the x component. So 25 times the sine of 53.13 is what I'm doing to get the x component. So 25 times sine 53.13 gives me 20. So the x component is in fact negative 20. Oops, I should probably write that in a color. Negative 20.00 newtons. The x component, or excuse me, the y component is going to be given by cosine. So that's 25 times cosine 53.13. And that gives me 15.00 newtons for C. So just in case you wondered about how that looked, let me draw it over here. This is 25.00 newtons. This is 53.13 degrees. This is C sub x, and this is C sub y. And that's where I got the cosine for the C sub y and the sine for the C sub x. Okay. Now I've got to do the green vector, which is D. So the green vector, notice that goes down and to the left. So it has a negative x component and a negative y component, as you can see, because if I go off this way, that's in the negative x direction, and then in the negative y direction. Similarly, if I did this first, that would be the negative y direction, and then this would be the negative x direction. So both of these numbers are going to be negative. And this time I'm going to take the sine of 60 to get the x component and the cosine of 60 to get the y component. So I'm going to take 40 times sine 60, and that'll give me the x component, which is 34.64 negative. And now I'm going to take 40 times the cosine of 60, and that gives me 20. So this is negative 20.00 newtons. And just so you'll know how that one worked out, I'll draw it over here in the green. And this, oop, I did that a little backwards. Let me adjust that. It's kind of backwards because I drew it one way and then I drew it a different way. I'm going to do this is 40.00 newtons. This is 60 degrees. And this is d sub x, and this is d sub y, and d sub y is 40.00 newtons times the cosine of 60.00 degrees, and it's going to be negative, and this is for negative 40.00 newtons times the sine of 60.00 degrees. So that's how I got all that. Now all I have to do is add the x components to get the resultant x component like this. So I'm going to say 10 plus 17.32 minus 20 minus 34.64 gives me negative 27.32. And now I'm going to do the same thing for the y component. That's 10 minus 10 plus 15 minus 20 gives me negative 5. So that's our resultant. Notice the x and y component are both negative. That's what we expect because it does look like the resultant vector has a very big x component and a very small y component. So now all I have to do is render this accordingly. I'm going to say this is 5 newtons, and I'm going to say this is 27.32 newtons. And then this angle right here is what I'm going to call phi, and that's the R magnitude there. So phi is going to be the inverse tangent of 5 over 27.32. Notice I didn't put any negatives in there. I don't want to do that. Tangent doesn't know the difference between the numerator being negative and the denominator being negative. It treats them both the same because a negative divided by a positive is a negative, and a positive divided by a negative is a negative. So it doesn't know the difference. There are, cosine and tangent functions in C and C++ that actually does have that property, but we're not using that. So I'm going to say tangent inverse of 5 divided by 27.32. And that gives me 10.37 degrees. That's not bad. I got 12.2 from just eyeing it, and I'm doing this on a slippery board, so that's not very bad. The R is just given by the Pythagorean theorem, so I'm going to take 27.32 squared plus 5 squared. That's going to give me 771.4 under the square root. So R magnitude is equal to 27.32 squared plus 5 squared. And that's going to give me 27.77 newtons. And we had gotten 27.45. So that's really pretty impressive how well we did. So I can finally say R, the resultant, is equal to A plus B plus C plus D. And that has a magnitude that is 27.77 newtons. And that is going to be at 10.37 degrees south of west. And that's just one of the many ways we could specify it. But now we have that quantity right there. We could also write, by the way, that R is equal to negative 27.32 newtons I hat minus 5.00 newtons J hat, which we could also write as negative 27.32 newtons, comma, negative 5.00 newtons. And notice this time I just wrote 2. You can do that as well. If I just see 2, I'm going to assume it's x and y. So I could break that vector up into x and y components with I hats and j hats, or I could use this little less than greater than symbol. Just out of curiosity, the percent error The percent error in the magnitude is equal to 27.32 newtons. I'm going to take the absolute value minus 27.45 newtons divided by the accepted value, which would be 27.32 newtons, and then times 100%. 27.32 minus 27.45. I think that's what I got the first time. 27.45. Yes, I did. Now I'm going to divide that by 27.32, and then I'm going to multiply it by 100, and that's going to give me 0.48%. The percent error in direction is equal to, we had 10.37 minus 12.2 divided by 10.37 times 100% gives me 10.37 minus 12.2 divided by 10.37 times 100. That in fact gives me about 17% error, 18% error. So that's not terrible. Again, remember, this surface is super slippery. It's really hard to deal with, but I'm not too sad about that. And by me doing this, you've now seen exactly how you go about adding vectors graphically. And I've also shown you how to add vectors numerically. So the numeric addition of vectors is just taking and breaking each of the individual vectors into x and y components, adding all the like components, in other words, all the x components added together to get the x component of the resultant, and then I add all the y components together to get the y component of the resultant, and then I have to, if for instance I gave you the vectors in magnitude and direction format, then you should expect to give me the answer in magnitude and direction format unless I specifically say otherwise. So the way we did that is then we plotted the x component and the y component. Notice I took the time to do that, uh, even choosing the fact that they're negative. So the 27.32 pointed to the left, the 5 pointed downward, and I drew a vector, the x and y components like that at 90-degree angles to each other. And then I also specified the angle. I took the Pythagorean theorem to compute the magnitude, but I took the inverse tangent to compute the angle, and I got 10.37 degrees for the angle and 27.77 newtons for the magnitude, and that's how you do it. Does anybody have any questions on that? Someone, excuse me, someone asked for the test on the seventh practice test. Would you recommend we get our slash use graph paper? Uh, for starters, this test on the seventh is only going to cover chapters 1 and 2, so you won't be adding any vectors on that. But the next test, you certainly would add vectors. I find graph paper helpful, but it's really not too terribly necessary because I usually don't ask my students in real time to do a vector addition graphically like I just did, but I do ask them to do them ones like I showed you earlier with just the head to tail and the tail to head vectors. You don't need to do any computing with that. You just draw them and complete the parallelogram. So really a straight edge, a clear ruler, for instance, would be a good thing to have, but that's pretty much it. Anybody have any other questions? All right. So the rest of this chapter is really about vectors. So you should learn how to decompose vectors into x and y components. You should need to be able to then build vectors out of x and y components. Notice when I added these vectors, I basically decomposed each individual vector into x and y components. I added all the x components to get the new x component. I added all the y components to get the new y components. And then I recompose those vectors using the components. So I drew the 27.32 pointing to the left. That was an x component. I drew the 5.00 newtons pointing down. That was the y component. And then I made a right triangle out of it. I used the Pythagorean theorem to find the distance or the length of the hypotenuse, which is the magnitude of the vector. And then I used the inverse tangent function to find the angle that I had specified as phi or phi. And that's recomposing a vector. So that's composing a vector out of its components. So this practice of adding, four or more vectors, and I chose four because that made sure I handled a vector in each quadrant. So, for instance, vector A was in quadrant one, vector B was actually in quadrant four, vector C was in quadrant two, and then vector D was in quadrant three. That's why I did four vectors, so you'd see how I had to work out whether the x component was positive or negative, whether the y component was positive or negative, and then how I used the angle from the vector to the nearest axis as opposed to just using 240 degrees or 53.13 degrees or whatever. I always take the angle between the vector and a near axis so that the angle is never over 90 degrees. Any questions on that now? All right, so we've got a few minutes left. The class is supposed to run till 7:40. It's 7:25. What I thought I would let you know is you have to be able to use your kinematic equations to solve projectile motion problems, and that's the other part of what Chapter 3 is about. Chapter 3 had section sub 3 sub 1 was vectors and scalars. 3.2 was addition of vectors, graphical methods. 3.3 was subtraction of vectors and multiplication of a vector by a scalar. And subsection 3.4 was adding vectors by components. Section 3.5 was unit vectors. And then from there on out is vector kinematics. So you need to know your kinematic equations. Let me restate them before we get rolling. So our vectors, our kinematic equations are, for instance, the average speed is equal to distance traveled divided by, well, let's go ahead and write it, traveled. I want to make sure you know it's the distance traveled. It's not the distance you are away from where you started. Okay, so that's the difference between speed average and velocity average. The velocity average is the displacement divided by the time taken, whereas the speed average is the distance traveled divided by the time taken. And someone asked a question, will the final exam be comprehensive of the whole class? Yes. In fact, this first face-to-face test is going to cover chapters 1 and 2, and the second face-to-face test is going to probably cover chapters 1 through 6, say. So every one of my tests are comprehensive, both the face-to-face ones and the online ones and the practice ones. So the more you take these practice tests, the more experience you're getting in chapter 1 and 2 every time you do it, because chapter 1 and 2 are going to be in all the subsequent practice tests because the practice tests are comprehensive as well. That's sort of the nature of physics. You really can't get around that. So it's just easier to just say, hey, all our tests are comprehensive, because what happens is if I saw on face-to-face test one that students couldn't do a particular type of problem, then I usually would look up that type of problem and put it on the second face-to-face test, just to make sure that everybody corrected that thing that they didn't know about. That's literally how I make it. And I'm not doing that to be mean. I'm doing that because physics, like chemistry and like engineering, is such a comprehensive subject. that there's literally no subsection in the book that you're allowed to just say, okay, well, I just don't understand that. I'll leave that to be. Well, you can do that, but that is always going to cost you points and it's always going to result in you being unable to do a certain type of problem. And that could be the very thing that ends up getting you fired or taken off of a project or not promoted, all sorts of stuff like that. So, because of the comprehensive nature of physics and chemistry and engineering, the physical sciences in general, yeah, all the tests are going to be comprehensive and you don't get to just skip a section. I had, for instance, one student that just was unable to learn how to add vectors, mainly because early on he was at a technical school and they taught him how to add vectors using his calculator. And because of that, he never really understood adding vectors. He could just do it. He could just do it with his numbers. And sure enough, he ended up failing my 241 class like 3 times. Then he finally got through 241 and then failed 242 again because he couldn't add vectors. Because it turns out adding vectors is not just a 241 thing. In fact, it's also AC circuits problem. When you go to work out AC circuits, you have to use vector addition rules for that too. So you just never get away from any one subject. So expect whatever your weakest part was on each test, make sure you correct that for the next test because there's some probability that it'll appear on the next test. Any other questions? Okay. So I said the average speed is distance traveled divided by time taken. The average velocity is the displacement divided by time taken. Now remember, when I say divided by, I hadn't taught you anything about dividing by a scalar on a vector. But remember, division by a scalar is just multiplication by the reciprocal. So in this case, we're going to take the displacement vector, which is the final position vector minus the initial position vector. That gives us a vector quantity. And then you're going to multiply that vector quantity by 1 over the time. And that would give you the x component when you multiply it by the x component. And you do 1 over time and multiply it by the y component. And that would give you the y component of the average velocity. So I'm also going to call this with a vector symbol over it, I'll say x final minus x initial divided by delta t, which is also equal to delta x over delta t. We also learned that V is equal to V0 plus AT. Remember, we got that from integrating A is equal to a constant and then using the initial condition that V at time t equals 0 is V sub 0. So I got that. And then if I integrate this, setting V equal to dx over dt, I get the equation x equals 1 half AT squared plus V0t plus x0. And then if I solve that V equals V0 plus AT for t and plug that in the x equals 1 half AT squared equation, then I get V squared is equal to V0 squared plus 2a x minus x0. So that's another kinematic equation. So there's 1, there's 2, there's 3, there's 4, there's 5, and technically I left off a couple important ones, specifically V is equal to dx over dt like that. But we normally, because the x implies just the x component, we would normally call that dr vector over dt. In other words, we don't use the x vector to locate something in space. Some books do, but most of them call it the r vector to locate an object in space. So if you take the derivative of the r vector with respect to time, then you get the velocity vector. I'm going to call that equation 6. These numbers are not numbers I'm going to refer to back and forth throughout the whole semester. I just wanted to put numbers on them here so I can refer to them as needed here. 7 would be A is equal to dv over dt, which also happens to be equal to d2r over dt squared. And I gave you another equation, specifically v bar is equal to v1 plus v2 over 2. And this is only true for a equals a constant. This is only true for a equals a constant. And this is only true for a equals a constant. Okay. All the other ones are true all the time, but that's the key point. Now, the other big thing that I think is most important about projectile motion, oops, I did not mean to do that. The other big thing, I tried to hit stop share and somehow it went there. The other big thing I want to show you is a wonderful little diagram that we use when we're starting to study projectile motion. Let me get there real quick. Vector kinematics, projectile motion. There it is. I should see it somewhere in here. Ah, here it is. So I'm going to share my screen right quick, and I'm going to show you the screen of the textbook. So this photo is probably the single most helpful photo. What we have here is a red ball and a yellow ball that were initially at the exact same height. And it was in a pitch black room. And then what they're having is a strobe light that comes on, let's say every tenth of a second. It goes blam, blam, blam. Each time that strobe light comes on for a tenth of a second, it leaves an image on of the picture. So what you can see is at t equals 0 seconds, the red ball and the yellow ball were both inside of the little gun mechanism at exactly the same height. If you wait until a tenth of a second later, you'd see there's a red ball here that you can't really make out too well, and then there's a yellow ball here that you can make out, and those two are the exact same height. If you go another tenth of a second, then you get to this red ball, which corresponds to this yellow ball. Notice those two are at the same height. A tenth of a second later, these two are at the same height. A tenth of a second later, these two appear to be at the exact same height. That's the important point. What I want you to understand from this photograph is gravitational acceleration, which is 9.80 meters per second every second, acts on all objects independent of their motion. So one object, the yellow one, was shot perfectly horizontally to the right, but it still fell the exact same distance after a tenth of a second as did the ball that was just dropped straight down. And then after 2/10 of a second, it was the same height as the other one after 2/10 of a second. The other thing is, if I were to even fire the bullet straight up or the ball straight up, then when I fire the thing straight up, the velocity is still going to change by 9.80 meters per second every second in the downward direction. So if my initial velocity was 10 meters per second, and I shot it straight up, after 1 second, it would have lost 9.80 meters per second. So it'd only be moving up at 0.20 meters per second per second. Excuse me, meters per second without the second per second. So, in other words, the velocity is always going to change by the same amount when the acceleration is a constant. Since the acceleration is a constant, 9.80 meters per second every second downward, that means in each 1 second interval, the velocity is going to be decreased vertically by 9.80. If you did in a tenth of a second, it's going to be decreased by 0.980. If you did it in a hundredth of a second, it would be decreased by 0.0980 meters per second every second. Okay. But that's the key thing, is to understand that the horizontal motion and the vertical motion are tied together by time, but they act independently of each other, because the vertical one is acting like you just dropped the ball, or maybe you threw a ball straight up if it wasn't fired horizontally. If it was fired horizontally, you're acting like a ball was just dropped. If it was fired upward at some angle, then you're acting like it's fired upward at whatever that y component of the initial velocity was, so that it's going to lose 9.8 meters per second vertically each second. But that's also going to happen if you were to drop it. So that's the big thing. We'll talk about that more, and I'll show you some examples of computing projectile motion. That is a good way, for instance, for you to learn how to do more kinematics because chapter three is requiring you to use kinematic equations all over again. So, if you've done, enough homeworks in chapters one and two, but you still feel like you don't know kinematics, well, by the time you finish chapter three, you're going to have enough experience with kinematics that you'll feel even better. So, everybody that hasn't chatted me your first and last name, please do so now. But you guys are free to go. I thank you all for coming. We will meet Wednesday for class, but you're not supposed to meet for lab for Wednesday. In other words, Thursday when we have our lab, there will not be a lab. Okay, you guys are to take your test online using Respondus Lockdown Browser and Respondus Monitor and a webcam, and you're going to take it online. Everybody has to take it Sunday, sometime between 12:01 a.m. on Sunday and 11:59 seconds p.m. on Sunday. You have to take test one face-to-face test using a webcam, Respondus Lockdown Browser, Respondus Monitor, and your computer, and it'll be online. You're going to take it. You're going to take photographs of your work. You're going to show me those on the Respondus Monitor before you take the photographs. You'll submit the test as like it's a multiple choice. You're just going to type in the answers, and that's all you're putting in the typed in portion. You're just putting the final answer with each question, and your work is going to be on the paper, neatly written, and you'll hold up the piece of paper in front of the camera and say, "Here's number one," and you'll show it so that I can see it through the camera and see all the parts. So you have to hold it close and make sure you show me the whole part, then flip it over, show me number two, and then flip it over, show me number three, and so on and so forth. And then you submit it, and you've got like 15 minutes after you submit it to email me those photos in PDF format. Email them to me, preferably email them to me. I'm not going to say text them because they'll crash with that much memory. But that's what you're going to do on Sunday. It's got to be done on Sunday. If something comes up and you can't make it Sunday, you need to let me know a priori. But if it happens and you don't know about it until Sunday morning, then you need to let me know within 24 hours because otherwise I'm supposed to drop you guys if you miss a test. Okay? Thank you for coming, everyone. I'll wait here till the last person leaves in case anybody has any questions, but you're free to go. Thank you, Nathan.
I I just wanted to confirm that you'll be able to make an announcement about that lab assignment from last
Yes,
week.
yes, absolutely. And I'm going to take a screenshot of what you said right there.
Okay. Thank you so much. Have a good day.
You too. Take care.
Hello, Professor. Good evening.
Yes. How you doing?
Good. I had a few questions. So, I just wanted to confirm with the due date for the syllabus signature that you have my email that I sent for the syllabus signature. I've been attempting to contact you, but I'm not sure if I have the right information. I think I followed
Okay.
all the syllabus requirements.
Let me hold on a second. I got my screen sort of locked up and trying to figure out which person's talking to me right now. What's your name again?
Yeah, sorry, it's Tanner
Tanner, gotcha.
Fitzgerald. Yeah.
Okay, yeah, and I remember seeing a Tanner email me, so I've definitely been getting your emails. It was just a matter I've been swamped all weekend. I had to do a lot of stuff for family and stuff here, but I'll double
Okay.
check real quick just to make sure. There is a spot where I'm going to send out an email to everybody and have you submit your syllabus form there. So just keep an eye out for that email. That's where I'm going to ask everybody to send it. It was supposed to already be open. Now I can't even find it. So I don't know what happened, but I'll post that and just ask you to post it there, and everybody will get full credit on it. It was supposed to be done by today. That's not a big deal. I'll make sure everybody's got it done. It looks like everybody turned it in anyways. So is there
Okay.
something else that I missed on that?
I had a couple other questions, but that was it for that.
Oh,
But
okay. Gotcha. Well, if you got more questions,
um,
I'm here for that too.
yeah, the lab three, I don't have in my module, I don't have the addendum and I don't have the videos that the normal lab paper requires for it. I also don't have a link for the 15, like the 3.15 version, because I think that was on the addendum. I can only see the newest 3.16 version. I don't know if that
Are
matters,
you
but
in this class, the 241-001B?
yes,
Okay,
yes,
that's
yes, I
fine. Let
am.
me double check something real quick then. So I'm going to go to modules. First thing I need to do is check, you are registered in here, so I'm going to check the grades, make sure your name's listed in there. Tanner Fitzgerald, yeah, you're definitely listed in here, so that's cool. And now I'm going to check, see what you're missing, because I did find out I'm missing some files. Christine told me that. If you Now, one thing you might be looking for is I do not make a separate canvas for my lab that I do for my lecture. I have one canvas section, and that covers lab and lecture. So if you look in the modules, and that's the first area you should go to in my course, is you log into Canvas, you click on my course, and then you click on modules over in the left-hand side. And let me show you what we're looking at here. So I'm going to share my screen again. So right now you're looking at the modules and you'll see chapter practice. That's where you can do your chapter practice. Here's your practice test. Here's your online tests. And here's where your face-to-face tests will be. There shouldn't be any available yet, but that's where that'll be. Now, if you scroll down, that's week one. And then you'll see week one lab module. Here's all the stuff for week one lab one. And here's all the stuff for week one lab two. Here's week two module. Let's see what's going on with week two lab module. So did you not see all this?
Yeah, but I don't have that lab 3 analyzing motion, the addendum. I don't have that. It's not visible for me.
Oh, it's not here either. I can see that right now. That must be something that recently happened. So now I'll publish it. Yeah, I just noticed it didn't have that there. It was there the other day, but it's not there now. I don't know how, but that's something dumb that I did, I'm sure. So now you have access to that.
Right, okay. The Does the addendum use different videos? Because in the normal lab, like the first question, for instance, asks me about a video of a bicycle, but like with the provided videos, I don't have that.
Yeah, so what Christine was just telling me is I had a place in my folder that just showed me the videos I was using, and I just pulled all these out. But according to her, I must have left some out. So there should be a bike video. In fact, she told me specifically the videos I am missing are, let's stop sharing here for a second. Oh yeah, she said the Velocity 1D AA movie, SUV, VE 1D movie, bicycle and truck. Yeah, so those are all videos that I'm missing. I'm going to go ahead and look for them right now while I'm talking to you, and I'll put them up. So let me see. I'm going to look under files. And I did tell her I'm also going to put the deadline back because that's a screw up on my behalf. That has nothing to do with you. So you'll have ample time. I'm probably just going to give you another week to turn that one in. But now I'm looking for those videos. So VEL1D, VEL1D, VEL1DD, AA. So here's three: VE1D AA, VE1DD, and VE1DE. I just put those up and now I'm publishing them because when you put them up, they don't necessarily publish. And luckily, they give me two or three buttons to hit every time. So that's really useful use of my time, valuable use of my time. I have to have a free fall. So I've got those three. Now I need a FF. Let's see if I can find that one real quick. Find like free fall dash C. That one's there now. So I got VE1D, VE1DD, VE1DE, F fall C. Also, are we just using the AirTrack 4 dock for the incline video? No, there should be an incline video as well. Let's see if I can find that real quick. AirTrack level incline. There it is. AirTrack 4. I think both of these are necessary. So I just put two more videos called Air Track 3 level track down and back and Air Track 4 incline up and back. I think those are the other two that I need or that you need. So hopefully that'll help you. Are you seeing those
Um,
now?
I am, yes, thank you.
Okay. Hopefully that takes care of it. And now I'm going to change the due date now too, because that's not cool to do to you guys. So I'm going to click on analyzing motion. I'm going to edit it. And I'm going to change the due date from June 2nd to let's do June 10th because the 9th you already have a due date. You already have a lab that's supposed to be due that time. So I'm making it June 10th by 11:59 p.m. So hopefully that's enough. If you find out that that's not enough time, you need a little bit more because of all the work, I completely understand. Just let me know and I'll take care of it. Truth be known, you're not going to get counted late anyways if you turn it in a day or two late because I don't count it late until I grade it. So what else
Gotcha.
can I do to you for you, Tanner?
Yeah, just for the test that you were just going over, you said like holding up after you take it, like holding up your scratch work. You
Hmm.
said we're doing that on the camera after we take the tests during in like
Yeah,
in
so
lockdown browser, and we also send you pictures afterwards.
yes, because sometimes the video is not clear enough to show work where I can easily read exactly what you had. I can tell what's there, and it's mainly just for me to make sure the document that you're sending me, which is what I'm going to use to grade your test, you showing it to me in the camera is me confirming that this is exactly what you had while you were in the realm where you weren't allowed to Google stuff and stuff like that. And I compare that to the video or to the photos that you sent me. And if they match, then I grade the photos that you sent me. If they don't match, then you get in trouble. And, I basically say it appears you've cheated or sent me something wrong.
Thank you, I appreciate it.
No problem. Does that help?
Yes, that answers all my question. Thank you so
Okay.
much.
No problem, Tanner. Have a good one. Good luck, bud.
You too.
Remember, we will meet again Wednesday, but until then, you got nothing.
Thank you.
You're welcome. How about Samuel or Mihak? Do y'all have any questions for me?
Yes. All right.
Go for it.
Can you hear me?
I can. Yeah.
Um, yeah, I've in the past had issues with Respondus. I I don't know if it's my computer or not.
Hmm.
But for my calculus class, I did that online as well, and I tried to use Respondus, and it
Hmm.
just went into like a loading loop. So
Uh,
I'll
Go ahead. That's
that's
a sort of a deal breaker with an online class. So either you have to get that corrected, or you need to check out. They have computers at the school that you can check
mm,
out for free. Or you could set up something with a testing center or somewhere on campus, one of the computers there, and use that. Any of those are acceptable as long as they can run Respondus Monitor and Respondus Lockdown Browser. But just know that if something like that comes up, we might have to force you to take it at a testing center with a proctor. Otherwise, you'd need to drop the course because there's no other way we can do it with online.
yeah, that's why I typically did it with proctors.
Hmm.
It's just that the proctors only go through
Saturday.
all of the week except for Sunday. So
If you have something like that, and let's say you can only get an appointment on Friday or you can only get an appointment on Saturday, let me know soon as like right today or tomorrow is the day that you should try to make an appointment and let me know if they can't accommodate you on Saturday. I know they can't accommodate you on Sunday. I don't think any of the testing center gives a Sunday date, but if they can accommodate you on Saturday or Friday, just let me know which one they do and I'll make sure it's ready for you on that time.
okay, I'll probably do something tomorrow, and I'll email you with basically what I sent them.
No problem.
Um, so
Yeah, just make
thank
sure
you.
you let me know when they clear it or when they say it's okay that you can attend on Friday or Saturday, so I know which day to have it ready for you.
Okay, yeah,
All right,
typically they're pretty good Saturdays because I went to them so often. So
good, good deal.
there shouldn't be
Yeah,
an issue.
I'd hate to have a problem. I hate it when my online students have to take something and then they have to go look and buy some other stuff. I don't want that. But I was told this semester from now on, I'm not supposed to make students do any proctoring. But if you can't run the software, then proctoring is really the only other choice. So let me know if I can
Yeah, I
do
don't.
anything else to help you.
Yeah, I don't have an issue with it. It's I'm used to it by
You
now.
you live close to one of the
Yeah, I'm like
campuses at
five
least?
minutes away from the Chesapeake
Okay.
testing from TCC. So
Gotcha.
pretty
No problem.
close.
If that doesn't work out, if it's inconvenient, just look for one of the computers that TCC will check out for you. That's another option. But as long as you're cool with proctoring, I don't mind doing it. It just makes it a little unfair to you if I make a test on a Sunday and then you have to take it on Saturday. That's kind of a bummer to you. So I feel bad about that. But the rest of them should be occurring on lab days. Uh, well, not for your class. For the NO2 it would be, but not for your class. So anything else, Sam?
Nope.
All right.
You have a nice day.
Well, thank you. You too. Have a good one, bud. Any questions, Mihak?
Yeah, I had a question. I
Yes.
think I put it in the chat, but I just had a question about, I guess, like the test submission. So I know I think like test is multiple choice just based on what I saw on Canvas. But I was just
Mhm.
kind of wondering if like the submitted work would be like graded based on accuracy or
Yeah, so it's not gonna be multiple choice anymore. I got rid of that last semester just because I discovered there was a lot of something inconsistent with learning going on with the testing. So the tests are no
got it.
longer going to be multiple choice. They're still going to be the same questions that you take in the practice test, but I'm going to change the numbers in them and then take away the multiple choices. So you have to calculate what the answer is and then submit it. So on the actual online test, there's just going to be a text box for you to type in the number with the units for the answer, and that's all you're supposed to put in. But you're supposed to show me your work on all problems except for ones that I say no work required. So you'll show me the work, and then, like I said, at the end of the test, when you're finished with it, the Respondus monitor allows you to show papers, and you're going to show me each page front and back of all your written work and any equation sheets you have and all that. And you'll show them to me slowly enough and close enough to the camera where I can see every square inch and everything that's written on it. And then you submit it, and you've got like 15 minutes to send me a PDF version of the work again. And then I'm going to grade the work for correctness, but also for partial credit. So if you start off each of your problems by writing, X0 is equal to this number with these units, and X final is equal to this
Mm,
number with these units, and then you write down the unadulterated versions of the equations that as they appear on the equation sheet, that alone will allow me to give you a lot of extra credit. So make sure you solve them that way and then work out the algebra, and then you can make a lot better grade than just. It used to be literally you got the right answer and then you got 100. If you got the wrong answer, then you got zero. So I don't want to do
yeah.
that either.
Got it. And my Zoom kind of cut out, but I think somebody was asking about the syllabus thing on Canvas. I was locked down before. I'm guessing that's like open a syllabus signature that we submit.
Yeah, so I'm gonna put the thing disappeared. I have a turn-in area like we have for our labs. There's a turn-in area that says syllabus turn-in. That's supposed to
Okay.
be there. So I'll open that back up and I'll send everybody an email to remind them, or I'll post an announcement and you just post it there. It's not going to count late or anything. Today was supposed to be the day it was done, but I'll do that, and that's all my fault. That's not your fault. So don't worry about that. Just post it when you get a chance, and I'll let you know if I don't have it after some period of time. I won't just drop you or anything like that.
Got it.
Okay.
And I guess last question. So I guess the best way that you'd say to like reforge tests is just going to be those practice tests, those quizzes on Canvas, and I guess mastering physics.
Yeah, really, it's more the mastering physics is supposed to help you learn a little bit more. Like if you don't get enough from my
Mm,
examples and the book examples, they have some very strong tutorial type problems. That's what the mastering's for. So it's supposed to improve your problem solving skills. But to be honest
yeah.
with you, the most important part, once you've learned how to solve the problems, is just the practice test, or like you said, the chapter quizzes if you want to focus on one chapter alone at a time. But the practice tests are generally 100% of the questions normally come from the practice test, but I reserve the right to take 20% of the points from some other source. I just haven't done so in years.
Awesome. All right. Thank you so much. Appreciate it.
No problem. Have a good one, Yak.
Have a good one.
You too.